The default assumption in the industry is that scaling artificial intelligence at the edge requires brute force compute. The solution to complex physical environments is usually framed as buying larger clusters and running heavier models. This assumption relies on a legacy architecture that operates in a strict linear loop. Devices capture raw sensory data, transmit it to a centralized cloud, feed it into a machine learning model, and wait for an answer. The immediate consequence of this loop is extreme bandwidth waste. Edge devices act as passive pipes, continuously streaming dense, unvalidated arrays of multi-megapixel imagery across networks that were never designed for that volume. That data transmission creates a secondary consequence, latency. Because the data has to travel to a cloud server to be processed, the round-trip delay renders real-time, autonomous coordination for edge robotics impossible. As those millions of pixels arrive in the cloud, they generate a tertiary consequence in the form of uncontrolled inference costs. Every redundant frame and noisy pixel demands expensive GPU cycles to process. Optimizing your downstream ML model or scaling up your cloud infrastructure does not solve this problem. Those efforts treat the symptoms, completely ignoring the root issue of how raw data is ingested and transmitted in the first place. Scaling edge systems requires governing the data and enforcing physical rules entirely before that payload ever reaches the intelligence layer. This is the exact mechanism built into ShelfCat. It is a multi-version, production-grade edge pipeline governed by a strict Rust backend designed to shrink and validate data well before any GPU cost is incurred. To build edge infrastructure that actually works, we have to decouple raw perception from downstream intelligence, putting an end to the transmission of millions of raw pixels over the network. ShelfCat accomplishes this decoupling through a mechanical process called semantic load-bearing compression. This animated diagram illustrates how ShelfCat's color-by-number filtering normalizes visual perception. A high-resolution pixel matrix is intercepted at the edge, compressed into basic geometric blocks, and translated into a clean text string. By systematically identifying and stripping away noise and redundant imagery locally, the filter ensures the data is strictly highly relevant before a downstream machine learning model ever touches it. The payload shifts completely. The system stops emitting bloated megapixel files and begins transmitting structured facts and highly compact messages. This architecture maps directly onto other heavy physical sensors, particularly acoustic data systems. Traditional audio systems fail for the exact same reason as vision systems. Constantly streaming uncompressed, raw audio waveforms across a network causes severe network congestion. An ET gating pipeline intercepts the audio feed the moment it is captured, running local filters to strip out ambient noise and irrelevant frequencies right at the hardware level. Instead of pushing a continuous sound file to the cloud, the system outputs a single verified acoustic fact, such as an alert reading glass break, zone 2. The math here is straightforward. Transmitting a tiny text string of an event requires a microscopic fraction of the network bandwidth compared to streaming continuous raw audio waveforms. By introducing structure before intelligence, the base unit of communication upgrades from heavy, ambiguous raw perception to highly actionable, bounded signals. Moving beyond simple compression, ShelfCat's version 4 Rust ingestion backend operates as a rigorous validation layer. This layer enforces shared geometry and real-world expectations. It mathematically verifies if a captured object aligns with known slot expectations or violates physical occlusion thresholds. Crucially, every single one of these physical constraints is enforced outside of the actual ML model. Measured, precise, this ingestion gate holds the ultimate authority. It decides whether expensive downstream inference is even allowed to happen. This comparison table outlines the stark contrast between traditional A100 or independent software vendor stacks and ShelfCat's edge pipeline. Looking at the communication unit disparity, GPU-first pipelines require entire raw images to function, while ShelfCat utilizes extremely lightweight, validated facts. On semantic, traditional pipelines rely entirely on whatever model is running to interpret the world, whereas ShelfCat strictly enforces physical rules at the ingestion point, ensuring uniformity. The financial impact of this architecture scales immediately. Eliminating unnecessary, ungated GPU work at the edge cuts artificial intelligence inference costs by 2 to 5 times. Because these rules are enforced externally, the system's outputs become fully auditable, they are highly deterministic, and consistently replayable for engineers. Cloud-heavy architectures are highly effective at running complex inference, but they fail completely at data governance. Establishing a pipeline that governs data before a cloud cost is ever incurred creates the actual technical moat for scalable platforms. The absence of a shared physical contract is why multi-agent networks fail today. Separate models constantly contradict one another because they lack a unified baseline for how to interpret the physical world. ShelfCat bridges this gap by acting as a pre-language layer for AI communication. Implementing deterministic gating forces every downstream component to speak the exact same ontology. This generates immediate operational benefits. Model embeddings align seamlessly, and subsequent reasoning chains can no longer hallucinate or contradict base physical laws. This diagram shows the most radical capability of a pre-language layer, true edge-to-edge communication. Edge node A verifies a fact and sends a lightweight packet directly to edge node B, bypassing the cloud entirely. In a concrete scenario, an edge camera identifies an empty slot and generates a high-confidence semantic signal representing that fact. A corresponding edge robotic agent receives that signal and immediately trusts the gated fact. It requires zero access to the original megapixel image to understand its environment. Removing the cloud latency loop enables nodes across a facility to synchronize state and coordinate complex actions with complete autonomy. Shared physical constraints establish a shared language. This is the only technical path to scaling distributed multi-agent intelligence in real-world environments. This system diagram outlines the complete end-to-end architectural flow of ShelfCat, moving from the local edge through Rust ingestion and outputting to multi-model inference. The pipeline rests on three technical pillars: semantic load-bearing compression to shrink the payload, out-of-model rule enforcement to guarantee validity, and a pre-language shared ontology to align downstream agents. This structure forces a massive collapse in bandwidth requirements, scaling alongside a 2 to 5 times reduction in raw inference expenditures. For infrastructure of this magnitude to be widely adopted, it has to earn the technical trust of ML platform operators and staff engineers. Securing that trust requires an open core or stewardship deployment model. Releasing the Rust ingestion, the gating logic, and the schemas as open source ensures total transparency, allowing engineers to verify the underlying math themselves. Simultaneously, retaining control over the advanced enterprise tooling and hardware certifications ensures the project remains economically sustainable without compromising the integrity of the core technology. ShelfCat is an iterated, production-grade pipeline with a proven migration history across multiple versions. The future of artificial intelligence simply does not scale by transmitting raw sensory data. It scales through compact, validated semantic signals.